Hello and welcome to this interactive presentation on correlation. I'm Professor Conrad. After this presentation, you should be able to explain the purpose of correlational research and identify characteristics of correlational research designs, identify the characteristics of a linear relationship between two variables using a scatterplot figure, describe the characteristics of a linear relationship between two variables using the sign and the numerical value of a correlation coefficient. Interpret the correlation coefficient as a measure of effect size. Conduct and interpret a hypothesis test using a Pearson correlation. Run and interpret a Pearson correlation test examining the bivariate relationship between two variables in SPSS. Create a simple scatterplot figure in SPSS Chart Builder. Report the results of a Pearson correlation test in APA format. Understand concerns for correlational research regarding causation, restricted range, and outliers. And finally, identify alternative correlation coefficients and be able to describe and identify example research circumstances in which each alternative correlation statistic would be used instead of a Pearson correlation. Unlike experimental research or group comparison research designs that examine differences between groups on a variable being measured, the goal of correlational research is to examine relationships between variables. When conducting correlational research, we are typically interested in the following two questions. Does a relationship exist between two variables? And if so, what is the nature of the relationship between those variables? The most basic of correlational research designs involves measuring two variables for each individual or participant in our sample to examine if a linear relationship is present between the two variables. To test for a linear relationship, the scores from the two variables being measured are examined using a correlation statistic. As an example, imagine we were interested in examining the relationship between the number of stressful events experienced by college students and their overall psychological health. In particular, we might predict, or our research hypothesis would be, that more stressful events experienced would be associated with lower psychological health scores. We have 25 college students fill out a stressful event checklist known as the Undergraduate Stress Questionnaire that has them mark how many stressful events they recently experienced out of a total of 82. We also administer them a 7-question psychological health screener and create an overall psychological health score out of 35, in which higher scores indicate better overall psychological health. The example data on number of stressful events and psychological health scores are presented here. Correlational data consists of measuring each participant on our two variables and forming two sets of numerical scores. One set of scores is labeled the X variable and the other set of scores is labeled the Y variable. In our example, the stressful event score is our X variable and the psychological health score is our Y variable. As shown here, researchers may present their correlational data in a graph called a scatter plot, which plots each individual's value on one variable X against the value of another variable Y as one data point. A scatter plot makes it easier to see, in other words, visualize and describe the nature of a relationship between two variables. Here we see a scatter plot for our research example that presents the X variable of number of stressful events on the X-axis of the graph and the Y variable of participants' psychological health score on the Y-axis. A point or dot is then placed for each participant in our sample at the intersection of his or her scores on the two variables. What does this scatter plot indicate about the relationship between our two variables? Well, the pattern seems to indicate that as the number of stressful events increases, psychological health score decreases. However, to better examine the nature of this relationship and determine whether the pattern we observe in the scatter plot is meaningful, we will want to calculate a correlation statistic. To statistically measure and describe a relationship between scores on two variables, researchers calculate a numerical index called a correlation coefficient. A correlation coefficient can range from -1 to 0 to +1. When interpreting a correlation coefficient, both the sign, whether it's negative or positive, and the numerical value tell us important information about the nature of the relationship between the two variables. The sign of a correlation coefficient indicates the direction of the relationship between the two variables. If the correlation coefficient is positive or above 0, then there is a positive relationship between variables x and y. A positive or direct relationship is observed when the two variables change in the same direction. As x increases, y also tends to increase. For example, there is a positive correlation between the amount of time a student spends studying for an exam and their score on the exam. As time spent studying increases, the student's exam score increases as well. If the correlation coefficient is negative, then there is a negative relationship between x and y. In a negative or inverse relationship between variables, the two variables change in opposite directions. As x increases, y tends to decrease. For example, there is a negative correlation between a student's level of test anxiety and their score on an exam. As the amount of test anxiety increases, a student's exam score decreases. Interpreting the numerical value of a correlation coefficient. The numerical value of the correlation coefficient indicates the strength or consistency of the relationship between the two variables. Regardless if the correlation coefficient is positive or negative, the closer the value is to 1, the stronger the relationship is between the two variables. Alternatively, a correlation coefficient near 0 indicates that the variables are not related or the relationship between them is very weak. A correlation coefficient of +1 indicates a perfect positive relationship such that for every increase in x, there is a consistent and predictable increase in y. For example, if you work a job that pays an hourly wage of $10 per hour, then there is a perfect positive relationship between the amount of hours you work and the amount you make. This relationship is shown in the scatter plot here. In the following video, we will provide some examples of interpreting different correlation relationships. In this video, we will briefly demonstrate how to use scatter plots to interpret the sign and strength of relationships and use them to visualize what different correlation coefficients look like. In this first example, we see a perfect linear relationship between variable x and variable y. We know this because a straight line can connect the dots in the graph. Also, each time variable x increases, variable y decreases. This tells us that the relationship is negative. Based on this visual, we would know that the correlation coefficient, or R, for this relationship would be -1. While our first example was straightforward, since it showed a perfect relationship, it can become slightly more difficult to interpret non-perfect relationships using scatter plots. How would we characterize this relationship in our second example, and what would we estimate the correlation coefficient to be? A good first step in helping us determine the nature of this relationship is to draw a circle or an envelope around all the data points in the scatter plot. The direction in which the envelope is pointing indicates the direction of the relationship. Additionally, more elongated and thinner the envelope appears, the stronger the relationship between the variables are. Alternatively, if the envelope is very round or appears to look like a chocolate chip cookie, this signifies that there is a very weak relationship between the variables. With that information here, we can tell that this example relationship is positive, since as variable x increases, so does variable y. This would also be a relatively strong relationship. Specifically, this is what a correlation coefficient of r plus 0.80 looks like. Keep in mind, this is a really strong relationship as it is close to 1. Although even though it's strong, the scatter plot may make it appear that the relationship is not exactly consistent. Now that we have the idea, how would you describe the direction and strength of this relationship? Well, if we draw the envelope around the dots, we first see that the direction is somewhat negative, since when scores on x increase, scores on y tend to decrease. Also, we can tell that this example relationship would not be as strong as our previous example, since the envelope is slightly wider. The correlation coefficient for this example then would be r equals negative 0.50. So negative because it's a negative relationship, and the strength is still moderately strong in this case. Let's take another example. What would you characterize the nature of the relationship for this scatter plot to be? Well, this is what a scatter plot would look like if there really was no relationship between variables, or a very weak relationship between variables. In this example, as we draw the envelope, we see no real directional pattern of the dots, and the envelope itself is very round and wide. This shows, in this particular example, we're showing an r of positive 0.05, which indicates minimal, if any, relationship between variable x and variable y. Let's try one more example here. How would you describe the direction and strength of this relationship? When we draw the envelope, we see that the relationship is slightly positive, but not as strong as some of the other examples we observed. In this case, the correlation coefficient of r would be positive 0.30. This is an important example because this is usually the size of the relationships we are trying to detect in psychology or other social science research. Notice the amount of noise that's still present in this relationship. This noise makes it difficult to discover these types of relationships, and usually requires careful observation and research methodology. Finally, I wanted to show you one more example because it presents a known limitation of using a correlation coefficient to examine a relationship. In this example, we plotted the relationship between arousal and performance. Research in many different performance domains has shown that a moderate amount of arousal is best for optimal performance. If we have too little arousal, we won't perform optimally, and if we're over-aroused, we also won't perform to our best as well. This relationship is so well established that it's referred to as the Yerkes-Dodson law. When we look at this scatter plot here, we can clearly see and describe that Yerkes-Dodson relationship. However, if we were to examine this through a correlation coefficient, we would discover that the r is negative 0.01. So if we had just looked at the results of the correlation statistic without examining the scatter plot, it might suggest that there would be no relationship between these variables. And this illustrates the important point that correlations are designed to test linear relationships. If we move over here and look at the character of this relationship, in this case, we observe a curvilinear or a U-shaped quadratic relationship between arousal and performance. So we can see it with our eyes in the scatter plot, and we can see it detected here as well. However, this would require different and more advanced statistical methods to actually measure and detect. As we return to our example correlational research question, what would we roughly expect the correlation coefficient R to be between the number of stressful events experienced and psychological health? based on the scatter plot, it appears that as individuals experienced more stressful events, their psychological health scores decreased. So this would be a negative relationship, and we would expect the correlation coefficient to be negative. What about the strength of the relationship? While the relationship is not perfect, there does appear to be a moderate to strong association between the two variables. As a result, we may expect the correlation coefficient to be around an R equal to negative 0.50. And in fact, when we calculate the correlation coefficient for this research example, we would find it to be negative 0.53. Next, we'll show you how we would calculate this correlation statistic. The Pearson correlation coefficient. The most commonly used correlation statistic is the Pearson correlation, also known as Pearson R or the Pearson product moment correlation coefficient. The Pearson correlation is identified by the letter R and examines the linear or straight line relationship between the two quantitative variables. The Pearson correlation is the appropriate statistic to use when you want to examine the linear relationship between two variables, or what's known as a bivariate relationship, and when both variables are numerical scores that are from an interval ratio scale of measurement. The Pearson correlation is not appropriate if you want to examine a nonlinear relationship between two variables, if one or both variables are nominal or ordinal scale of measurement, or if you want to account for or control for a third variable. Pearson R is a ratio that is conceptually determined by taking a measure of the covariability of x and y in the numerator divided by the total amount of variability in x and y separately. Covariability is the extent to which both the x variable and the y variable change together or vary with one another. If the covariability is high, then this will explain much of the overall variability present in the variables, and we would expect the ratio computed for R to be close to 1. Since R is a ratio or proportion out of the total amount of variability, the value for R can never be greater than plus or minus 1. As we showed before, a Pearson R of 1 is a perfect relationship where the covariability observed between x and y accounts for all the variability present in the two variables. To calculate this ratio for Pearson R by hand, we would use the following formula. The term in the numerator is referred to the sum of the cross products and is used as our index of covariability between x and y. In the denominator, we multiply the separate sum of squares for each variable and then take the square root. However, we will use SPSS to perform this computation and focus on the use and interpretation of the correlation statistic. Using and interpreting a correlation statistic. There are two distinct ways we could go about evaluating a correlation coefficient when we want to interpret if a relationship is present between two variables. First, we could use correlation as a measure of effect size about the strength of the relationship between two variables. Alternatively, we could conduct a hypothesis test and examine the statistical significance of the correlation. We will review each method of interpretation next. Correlation coefficient as a measure of effect size. The correlation coefficient R describes the degree or consistency of a relationship between two variables. Researchers will often calculate the coefficient of determination, or R squared, by squaring the correlation coefficient to use as a measure of effect size about the strength of the relationship. The correlation coefficient tells us the proportion of shared variability between the two variables and can inform us how much of the variability we observe in variable y can be predicted by variable x. Functionally, we can use either Pearson R or the coefficient of determination R squared to understand the strength of the relationship by using Cohen's effect size guidelines. A small effect would be equivalent to an R of plus or minus 0.10, which equates to an R squared of 0.01, or about 1% of shared variability between the two variables. A medium effect of a relationship would be an R of plus or minus 0.30, which is the same as an R squared of 0.09, or about 9% shared variability between the two variables. Finally, a large correlation or a large relationship would be an R of plus or minus 0.50, which is the same as an R squared of 0.25, or about 25% of the variability accounted for within the two variables. Importantly, using effect size criteria to evaluate the correlation allows us to interpret how meaningful the linear relationship between variables appears to be, independent of the sample size and whether or not the correlation was statistically significant. Testing if a correlation is significant. The second approach to interpreting the relationship between variables is to evaluate the statistical significance of a correlation coefficient by conducting a hypothesis test. Testing the significance of a correlation will result in one of two decision outcomes. If the correlation was found to be significant with a p of less than 0.05, then we can be confident the relationship exists in the overall population. In other words, we would conclude that there is a relationship between the two variables. On the other hand, if the correlation was found to be not significant with a p greater than 0.05, then there is not enough evidence to conclude that a relationship exists in the population. In this case, we would conclude that there is no relationship was found between the two variables. All else being equal, a stronger correlation coefficient, one that's closer to plus 1 or minus 1, is more likely to be found significant. Examining the statistical significance of a correlation will follow the same hypothesis testing procedure we use for other inferential test statistics. Since we'll be using SPSS to perform the calculations of our correlation statistic, we can use a simplified three-step process for conducting the hypothesis test. In step 1, we would simply state the null and alternative hypotheses. The null hypothesis for a correlation hypothesis test states that the population correlation, or the Greek letter rho, is equal to 0. This would mean that there is no relationship between the two variables in the population. The alternative hypothesis states that the population correlation of rho is not equal to 0. This would mean that there is a relationship between the two variables in the population. The second step would then be to compute the Pearson R test statistic in SPSS and obtain the exact p-value. And then finally, in step 3, we would make a decision based on that p-value. If the p-value is less than 0.05, then the correlation is significant, and there is a significant relationship between variables. If the p-value is greater than 0.05, then the correlation is not significant, and we would fail to reject the null hypothesis and conclude we do not have evidence for a relationship. A note about the p-value for correlation statistics. The probability, or p-value, for a calculated Pearson R coefficient indicates the likelihood of observing a correlation coefficient with a numerical value of that magnitude from our sample data if there was no correlation in the population. In other words, if there really was no relationship between the variables. Students often confuse the Pearson R coefficient and the p-value because they are both stated proportions. So let's try to simplify what each is telling us to make sure we can interpret test results correctly. If we assume that two variables are not related, then we would expect to find a correlation between these variables to be close to 0. In other words, there is a high probability we would obtain a small correlation coefficient from our sample data when no relationship exists. Alternatively, there is a very low probability we would obtain a large correlation coefficient from our sample if no relationship actually exists in the population. As a general rule of thumb, when the correlation coefficient R is small or near 0, then the p-value will likely be large and the correlation will not be significant. As the correlation coefficient R increases, then the p-value decreases. As a result, larger or stronger correlation coefficients are more likely to be found statistically significant. Example Pearson correlation test. Using our research question examining the number of stressful events experienced by students and seeing whether or not that's related to their psychological health, let's conduct a Pearson correlation test. Our first step would be to state the null and alternative hypotheses. In this case, the null hypothesis would state that the population correlation rho is equal to 0, or that there is no correlation or no relationship in the population between the number of stressful events students experienced and their psychological health. The alternative hypothesis, which in this case would be a two-tailed or non-directional hypothesis, would state that the correlation coefficient of rho does not equal 0. This would mean that there is a correlation, or there is a relationship in the population between the number of stressful events experienced and students' psychological health. Our second step would then be to compute Pearson R test statistic and obtain the exact p-value in SPSS. We'll show you how to do this in just a moment, but here you can see the generated SPSS output looking at the correlation between the number of stressful events college students experienced and their psychological health. The output gives us three specific pieces of information. First is the Pearson R correlation coefficient, which in this case was negative 0.530. You also see two asterisks or stars by that number, which is SPSS's way of telling you that the correlation is significant. In this case, two asterisks meaning that it's significant at the 0.01 level, so even more highly significant than the 0.05 level. We can also see the exact two-tailed probability or significance for this correlation, which again tells us the likelihood of observing a correlation coefficient this large if there really was no relationship in the population. So in this case, the exact p-value is 0.006, which is significant. Lastly, they give us the n, or the number of participants that were included in the correlation analysis, which was 25. We also generated an SPSS scatter plot to visualize the data. A nice thing about the SPSS scatter plot is when you plot the regression line, or the line of best fit, it also gives you the R-squared value as a measure of effect size. From there, we can take this data and move on to step 3 and make a decision based on our p-value. So first and foremost, part 1 of this decision is to determine whether or not that correlation is significant. In this case, the Pearson R of negative 0.53 for a sample of 25 participants had an observed p-value of 0.006, which is much less than 0.05. So the correlation is significant, meaning we would reject the null hypothesis and conclude that there is a relationship. So part 2 then is to make an interpretation or draw a conclusion based on this decision. So we would say that the results showed a significant negative relationship, such that as the number of stressful events experienced by college students increased, their psychological health decreased. We would then report that as R equals negative 0.53, comma, N equals 25, comma, P equals 0.006, comma, two-tailed. We would also want to report a measure of effect size to show the strength of that relationship. So we could continually report that the coefficient of determination of R squared equaled 0.28, which is a strong relationship and indicates that the number of stressful events experienced shared 28% of the variability with psychological health score. As shown in the SPSS video on correlation and constructing a scatter plot, here is an example of reporting the results of a Pearson correlation test. When we report the correlation coefficient in the text, we want to report the correlation coefficient R equals, and in this case our obtained correlation coefficient was negative 0.53. We would then put a comma and then present the obtained p-value. So p equals 0.006. And in this case, comma, two-tailed, letting the reader know that we conducted a two-tailed test. It's also helpful to report and interpret the correlation or the coefficient of determination, or R squared. In this case, we had an R squared equal to 0.28, which represents a strong effect and indicates that the number of stressful events experienced shared 28% of the variability with psychological health scores. Finally, when reporting multiple correlations, it is usually more helpful to report these in a correlation matrix, which is a type of table, and this is demonstrated and shown here. Limitations of correlational research. The next step in understanding correlational research is to go from running and reporting the correlation to interpreting what the finding means in the context of our research question. As a researcher, it is important that we do not assume beyond what a correlation can tell us when interpreting a significant correlation. Specifically, when interpreting the findings of our correlation statistic, we must consider three important limitations of correlational research. First is the problem of outliers. Outliers can influence the value of the correlation coefficient. Second is the problem of range restriction. Limiting the range of scores on one variable being measured can influence the value of the correlation coefficient observed. Third, and most cautiously, we need to remember that correlation does not imply causation. Correlational research cannot establish a cause and effect relationship between variables. We'll cover each of these limitations in more detail next. Outliers. The presence of an outlier in your correlational data can greatly influence the correlation coefficient you observe. As illustrated in Figure 1 below, imagine we first examine the correlation between the number of stressful events and psychological health in a sample of 11 participants. If we examine the correlation, in this case, we would find a significant correlation of R equals negative 0.76. However, you may also notice that one score has an unusually high number of stressful events experienced and an unusually low psychological health score. If we were to remove this case, as shown in Figure 2 below, we would no longer observe a relationship between the variables, and the R would be equal to 0.02. This shows the importance of screening your data for potential outliers that may influence your correlation statistic. In addition to leading you to believe there is a relationship present when one likely does not exist, outliers could also lead you to conclude there is no relationship between variables when a relationship might actually be present if the outliers were removed. Finally, outliers will exert a greater influence on correlation coefficients when the sample size is smaller, as was the case in this example illustrated here. A second limitation of correlation is the problem of range restriction. In addition to being affected by outliers, the value of the correlation statistic is highly sensitive to the range of values represented on each of your variables being measured. An example of the problem of range restriction can be observed when looking at the relationship between college aptitude test scores, like the SAT, and students' college GPA. Higher SAT scores are predictive of college success, and this is why scores are used for admissions criteria. However, as shown in Figure 1, if we were to look at the relationship between SAT scores and college GPA for students admitted to Ivy League schools that needed a cumulative SAT score of 1400 or better, we might conclude that there is no relationship between SAT scores and college GPA. This is because the range of SAT scores represented in the data is highly restricted. In other words, all students had really high SAT scores. As shown in Figure 2, if we were to examine the same data and include a more inclusive range of scores representative of students that were admitted to college, we would observe a rather strong correlation between SAT scores and college GPA. Examining the relationship between SAT scores and college GPA scores among those students admitted to college may even restrict the range and reduce the strength of the observed relationship because the sample does not include students with low SAT scores that were not admitted into college. Overall, to get the most accurate sense of the correlational relationship between two variables, a researcher would want to collect data that includes the full range of scores on each measure to the extent this is representative of the population of interest. The ability to detect a relationship can be obscured when the range of one variable is restricted. Also, if the range is restricted because the sample was drawn from a specific population, such as college students, then inferences about the observed relationship should not be generalized to a broader population. For instance, we should not conclude that because we did not find a relationship between SAT scores and GPA in students admitted to prestigious institutions, that SAT scores are not predictive of general college student success. Limitation number 3, correlation does not imply causation. A methodological limitation of correlational research is that it cannot establish a cause and effect relationship between variables. Correlational study designs and statistics can only be used to establish if there is a relationship between two variables. They should not be interpreted as evidence for why the two variables are related to one another. As shown here, a significant correlation could be observed for a number of reasons. Returning to our correlation example, it would be false to conclude that because we found a significant negative correlation between number of stressful events and psychological health, that experiencing more stressful events caused a decline in students' psychological health. Based on our study methodology, it is just as plausible that lower psychological health caused students to experience more stressful events. In other words, our Y variable was the underlying reason we saw the change in X. Moreover, it is equally plausible that a third variable that we did not measure is the reason we observed the relationship in the first place. Correlational study designs do not allow the researcher to establish temporal precedence, namely that the variable thought to be the cause came before the effect, and do not allow the researcher to control for third variables, known as extraneous or confounding variables. Therefore, correlational findings cannot be used to make cause and effect assertions. Instead, only when a true experiment is used that manipulates an independent variable and controls outside variables can a researcher draw cause and effect conclusions. Finally, this presentation focused mainly on the commonly used Pearson correlation. However, using an alternative correlation coefficient to Pearson R is necessary depending on either the nature of your research question or the type of data you are using. The different correlation statistics or coefficients, when each is appropriate to use, and an example are summarized in the table here. The Pearson correlation, or Pearson R, should only be used when examining the linear relationship between two numerical variables that are on interval ratio scale of measurement. For example, we would use the Pearson correlation if we wanted to examine the relationship between students' test anxiety on a numerical scale and their test scores in the class. Partial correlation is appropriate to use when examining the linear relationship between two numerical, in this case interval ratio variables, while also wanting to control for or holding constant a third variable. This would be like examining the relationship between students' test anxiety and test scores while also controlling for the amount of time spent studying for the test. In this case, it may be that students' test anxiety is a result of not being prepared enough for the test. So in order to control for this additional factor, we might measure the amount of time students spent studying for the test and include this as a controlling variable or a constant to see if the relationship is still present. For the Spearman's row correlation, we might use this in a couple of different scenarios. First, Spearman's correlation should be used when examining the relationship between two ordinal scale of measurement variables. So this would be, for example, like examining the relationship between low, medium, and high test anxiety and test grade that wasn't numerical, like A, B, C, and D, and F. So obviously there's ordinal qualities to that, but not interval scale ratio of measurement. The other time we might opt to use a Spearman correlation would be when examining a directional but non-linear relationship. So for example, we may opt, instead of a Pearson correlation, to use a Spearman correlation if we wanted to examine the relationship between the amount of time spent studying for a test and test scores, because there is a kind of a law of diminishing returns regarding the amount of time students might spend. So once you reach a certain threshold of hours spent studying for the test, each additional hour might result in little gain on your test score. So that would be an example of a non-directional relationship. We may opt to use the Spearman correlation examine instead of a Pearson correlation. Another example is either the point biserial or biserial correlation. We use one of these two when examining the relationship between one nominal dichotomous variable, in the case of a point biserial, or just a nominal categorical variable that is continuous in the case of a biserial correlation, along with one numerical interval ratio variable. So this would be like examining the relationship between students who attended a test review session, they either attended or did not, in students' test scores. In many ways, this would be very similar to an independent samples t-test, but only we're looking at a relationship and not necessarily looking at mean differences. Finally, the phi coefficient would be used when examining the relationship between two nominal dichotomous variables, in other words, two categorical variables. This might be used in our example here if we're examining the relationship between test review attendance, whether they attended the review or not, and whether or not they passed the exam, so either passing or failing the test. In summary, correlational research evaluates the nature of a relationship between two variables. A correlation coefficient is a statistical measure of the relationship between variables that ranges from -1 to +1. The sign of the correlation coefficient indicates the direction, and the numerical value indicates the strength of the relationship. A statistically significant correlation provides evidence that there is a relationship between the two variables in the underlying population. A correlation can be interpreted as a measure of effect size by calculating the coefficient of determination, or R². This can be used to understand how meaningful a relationship is independent of sample size and statistical significance. Problems with outliers and range restriction in data can greatly influence correlational findings and lead to inaccurate conclusions about relationships between variables. A significant correlation only shows that there is a relationship between two variables and should not be interpreted as one variable causing another. Finally, a Pearson correlation is appropriate when examining the bivariate relationship between two interval ratio scale variables. Alternative correlation statistics should be used when variables are measured on a nominal or ordinal scale, when the relationship is nonlinear, or when attempting to control for a third variable.